Hello everybody, I'm Matthew Paris, I'm a PhD student in architecture, and the work I'm going to present to you as part of this congress is called Impact of Morphology and Vegetation on Housing Estate Sustainability. I did in collaboration with Marianne Sansen, Stéphane Bosque, and Philippe de Villers, who work in the research laboratories of the National School of Architecture of Montpellier. I would like to start this presentation by introducing in its context a case study which is located in Languedoc-Roussillon, today called Occitanie, a region of the French Mediterranean coast, and which has been one of the most dramatic examples of urban sprawl in France, mainly from the 70s to the 90s, and which still continue today. The explosion of the city, which has been published in 2005, analyzed the different processes which took place in 13 metropolitan regions of the southern Europe. The concept of metropolization of the territory was then defined by Francesco Indovina in order to precise common trends and local specificity of these regions. A key element in the territory of Occitanie is the type of housing, and more precisely the importance of the single-family house. The intensity of urban sprawl is deeply linked with this type of housing. Housing represents around 40% of artificialized land, so finding sustainable alternatives to freestanding single-family houses is now a major goal for architects. The creation of new projects has to be dealt with a higher density. The evolution of the architectural morphology has to evolve towards kind of forms in order to reduce or even stop the process of sprawl in the territory. The process of densification of existing suburban areas has to be studied and examined through the prism of climate change and their impact of urban heat island. We need now to work on the evolution of the usual instruments and tools in order to improve the knowledge of their impact on the reduction of temperatures in relationship with their architectural and urban morphology. This presentation aims to look at the influence of the two main calculation methods used in simulation tools in order to model mean radiated temperature in peri-urban spaces. The first method used in Riemann software is based on the formula of integral measurement of the radiative fluxes defined by Peter Hope in 1992. The second method used in Ladybug tool software consists in weighting the surface's temperatures with the corresponding form factors. Starting from in situ measurements during a typical summer day, these two methods are applied to one street. The results of numerical simulation are interpreted through surface temperatures and mean radiant temperatures. Outdoor thermal comfort is analyzed quantitatively through the physiological equivalent temperature to study the impact of morphology and vegetation. Finally, the use of simulation tools to improve the thermal comfort in summertime in outdoor space of middle density housing estates will be discussed. The case study is called the Greek Village. It's a grouped individual holiday housing in Port-le-Cat and was built in the 60s by Georges Candelis in the frame of the touristic projects of the Mission Racine. The village is located between the pond and the Mediterranean Sea at an altitude of 4 meters. Previous research has demonstrated that is a fundamentally different morphology from a traditional urban downtown morphology. The buildings only have one ground or first floor and are often separated from the pedestrian street by a courtyard. The on-site measures were organized on two levels. First, a thermal walk in the morphology looking for cool spots in order to narrow down the research area. Then, a street measure in order to characterize the street's microclimate. A thermal walk wandering and exploring allowed to detect, verify and confirm the neighborhood cool spot. The selected street is then a north-south oriented street. This pedestrian lane is bordered on both sides by I and discontinuous H. For the street level measures, temperature, humidity and mean air speed are monitored every 5 minutes at the height of 1 meter on 6 strategic spots. Those are selected concerning different street section and orientation, tree vegetation and connection to courtyards. The Riemann model is Windows-based software. The model offers estimation of surface temperature of the ground and mean radiated temperature at a height of 1.1 meters. The model divides the three-dimensional environment into an upper and a lower hemisphere. The lower hemisphere is covered by only one solid surface. For this one, the albedo is known in order to simulate the short and long wave radiation. An albedo of 0.34 corresponding to a terracotta tile is used in this study. For the upper hemisphere, the distribution of the solid and free sky elements are required for the estimation of the radiation fluid density. These elements are attributed through a fisheye photograph. The geometric model that served as base for simulation was developed using NURBS 3D. The village breaks within the street of interest were modeled explicitly with high geometric detail. Surfaces temperatures of building, courtyard, vegetation, and ground were modeled using energy plus simulations through Ladybug Tools plugin. The surfacings were no larger than 2 per 2 meters square, ensuring a minimum resolution of surface temperature variation. Smaller surfaces dimensions were used for the ground in order to separate the different types of soil like terracotta or natural and edges that are key elements for this kind of morphologies. In this figure, we present the result of site measure. The dashed line corresponds to the wind and the solid lines to temperature, while the black arrows correspond to wind direction. The measured wind speed in the alley are much lower than those given by Meteor France, because the build morphology protects pedestrians well from strong winds. The measuring points can be classified into two groups. Points 3, 4, and 9 have wind speeds between 0.5 and 1.9 meters per second, whereas for points 1, 2, and 7 the wind speed is much slower and less than 0.5 meters per second. The coolest points are point 3 and 4, because they have the smallest sky view factors and wind high speed. Point 2 is one of the most uncomfortable spots. The sky view factor is the highest, and there's absence of edge on the side of this point. Mean radiant temperatures have been simulated with the data of the radar station for the relative humidity and the air temperature and with the measured airspeed. Then two behaviors are observed. For the two spots 2 and 7, TMRT starts at a high value, increase slightly, go through a maximum, then decrease. For these two spots, the curves show that the inertia of the floor covering material is not considered. For the 4 other spots, TMRT start at a moderate value, increase, go through a maximum, then decrease. What differentiates the 4th spot is the time during which TMRT remains close to the maximum. Only 1 hour for point 3 and between 4 to 5 hours for point 1, 4, and 9. Surfaces temperatures of building, courtyards, and the ground were modeled using Energy Plus simulation. The surface temperatures curves obtained with Energy Plus have a much more regular shape with illustrated consideration of the thermal conductivity and inertia of terracotta tiles. In the figure, the solid line corresponds to simulated temperatures with Rayman and the dashed lines to simulated temperatures with Ladybug. The maximum surfaces temperatures computed with Energy Plus are higher than the computed with Rayman. The most important differences are obtained for point 3, 4, and 9, which shows a different consideration of the air velocity between the two simulation tools. The time at which the maximum surface temperature is almost identical regardless of the simulation tool used. Now we'll discuss the result with this figure where the solid line corresponds to the PET calculated with Rayman and the dashed line with Ladybug. PET calculated with Ladybug are unrealistic due to the very high TMRT. Indeed, PET is very sensitive to this input parameter, so for discussion we will only remember the PET calculated with Rayman. The results show the importance of the wind accessibility in the street on the comfort felt. Point 3, 4, and 9, for which the airspeed is greater than 0.5 meters per second, are the most comfortable points. At no time during the day, point 3 and 9 are in the very hot zone, because these are 2 points which the air velocity is the highest. On the contrary, point 7, which is most of the time in the very hot zone, have no air velocity. Finally, point 3 is the most uncomfortable point. This may be explained by the very irregular layout of first floors. Point 3 is the only one that is protected from the sun, south side by the first floors of the two houses. In addition, this point is surrounded by edges 2 meters high on each side of the street. Given the proportion of housing in the territory sprawl process, finding sustainable alternatives to freestanding single-family houses is now an obligation. Terraced houses, semi-detached houses, patio houses are the kind of alternatives which are useful to consider today. The case study of this research, the Greek village, represents a sustainable alternative to sprawl by its higher density and a reduced artificialization of soils thanks to its pedestrian scale. The results obtained by the two simulations give very high physiological equivalent temperatures and a generally poor level of comfort. After all, while the sensations experienced during the measure campaign were much better, PET is very sensitive to the input parameter TMRT. So now we need to work on the evolution of the usual simulation instrument and tools in order to improve the consideration of edges and their impact on the reduction of temperatures in relation with the architectural and urban morphology. Therefore, the inaccuracy of simulated TMRT in relatively green microenvironment is mainly responsible for the inaccuracy of simulated PET. In addition, The very long calculation time required to simulate precisely complex and highly vegetated morphology represented an obstacle to the use of simulation tools in an architectural design process that requires back and forth. Thanks for your attention.